General Physics 1. And now, here's your professor, Varanga Pereira.
Hello everyone, welcome back. So we are going to finish off today talking about rotational motion for a moment, and then we're going to switch over and talk about momentum, collisions. We left off with a problem last time involving combining the different Newton's laws, right? So we have the one for the linear case, we have the one for the rotational case, and so we left off in a problem that will mix the two together. We'll finish that off, and then we'll talk about momentum in a bit more detail, which is something you've kind of been exposed to because that's in Newton's second law. And we'll get into how you can apply it in the specific case of collisions. So looking at this picture here, this is a test that many cars go through, right? So your car included. We'll go through these tests to make sure that in a case of the collision, the passengers are safe, right? So what we want to do is start thinking about what happens during a collision, and also why do we have airbags, right? So hopefully none of you have been in an accident like this, but airbags are there for your safety, right? So if you've seen maybe a car on the highway that has been under some sort of collision, you probably have seen maybe these sorts of airbags that have popped out. And what's their purpose? That has to do with momentum, right? It has to do with the things that we're talking about in the class. So let's take a look at this video where you kind of see the collision and the tests that they do for cars. And we'll play this and we'll talk over it, just to describe what's going on. So Insurance Institute for Highway Safety. These are the folks who do these sorts of tests, right? So you can see there's a crash dummy in the driver's seat, right? So there's paint on the different surfaces of the body there, right, to show where things collide, right? Without an airbag, with an airbag, right? So intuitively, you probably know that having an airbag is good. So if you compare, right, side by side, what happens without an airbag versus with an airbag. This has to do with momentum, so start thinking about the car having a certain momentum. It's changing its momentum, right? When it collides with the wall, it collides with another car. How does that happen, right? So we'll talk about linear momentum in a little bit more detail. We'll talk about this thing called impulse, which is connected to Newton's second law. And we'll talk about the conservation of linear momentum, when linear momentum doesn't change in a system, right? And we'll talk about collisions. We'll talk about one-dimensional collisions, multiple dimensions, collisions in multiple dimensions. Okay, so that's all up ahead. What we're going to do is jump back to where we left off last time with this problem, right, where we had a disk that was fixed at a certain point, no friction to worry about, some sort of bearing that will let the disk spin without interfering with it, so the disk will spin. There is this object hung on the side, right? So what we're trying to do is to find the different accelerations, the angular acceleration of the disk, the acceleration of the mass, the box, and then the tension that's on this cord, right? So we left off drawing free body diagrams for the box and the disks, right? So we made sure that the box had all its forces. We looked at the disk and put all the forces, right? So yes, you might be thinking about torque, right? So there's there's a force applied over some distance. There's R cross F, right? There's a torque. But when you're drawing free body diagrams, it's only external forces that you put down, right? You don't put accelerations, you don't put torque, you don't do any of that, right? So only the forces go on there. So just be aware of that, careful about that, right? Okay, so let's continue doing this, right? So once you have the free body diagrams, you know what to do, right? We apply Newton's laws. In the case of the box, all you have to do is apply the linear Newton's law. And particularly, it's only in the y direction, right? So the x direction doesn't have any forces. You could write it down just for completeness, but you don't really have to. So if we sum the forces in the y direction, well, what's there? Tension in the positive direction, so positive tension. Weight in the negative direction, minus mg, is equal to, right? Now we have an acceleration. It's not zero, right? We know that in this setup, if you imagine setting this up yourself, if you hang this weight and let go, this disc will start spinning, this mass will start falling, right? So there is an acceleration. So we can't set F equals ma to 0. We set F, right, sum of the forces equal to ma. When you know the direction of the acceleration, right, in the case of this, you can kind of say, oh, okay, I know this is going to go down, right? You should go ahead and put the negative sign there because it's a negative acceleration, ma. If you forget this negative sign, it's not the end of the world. Get to the end of the solving Newton's second law, and it will become apparent by what you get that there was a sign error, right? That this is really tricky. It's oftentimes the sign of MA can be confused, right? So don't worry too much about it. All I would kind of recommend is look at the problem, make sure you have a coordinate system set up, and if you know the direction where this is going to go, right? We know it's not going to go up, right? Then we can go ahead and put that negative sign because the acceleration is downward, right? So that would be kind of my recommendation to doing that. There's different ways to do that. Some people might make this coordinate system flipped so that the acceleration downward is positive, so then you don't have to put this negative sign. You have a few options there. This is kind of my way of doing it. It's not the only way to do it. So if you look at different people solving the same problem, they'll do it slightly differently. Just be aware the minus sign can be a little tricky, but I wouldn't worry too much about it, right? It will be apparent that there was a minus sign error somewhere once you get to the end, if you did make the error there. Okay, so now what we can do is solve for the tension, right? Which is something that we are asked to find. So then we can move the mg over, so we have minus ma plus mg, okay? So to solve for tension, we need to know the acceleration. We don't know the acceleration, right? So we have to kind of pause here and say, okay, we don't have enough information just from this free body diagram and this application of Newton's second law to finish this and get the tension outright, right? So we have to wait and figure out what the acceleration is. Luckily, we have another free body diagram to work with, right? Okay, so in this case, with the free body diagram, you can go ahead and do Newton's second law in the linear case, right? Because there are forces in the y direction, right? So the sum of the forces in the y direction. In the case of the disk, we know the disk has no linear acceleration. The disk is not falling, right? So then when you do sum up the forces in the y direction, let's use a different color. So we're going to sum the forces in the y direction in this case. That should equal 0. Once you sum that, there is no acceleration. Okay, so you can do this. I'm going to skip ahead because it's not going to give you the information you are actually looking for. Go ahead and do that, right? Sum the forces. This is negative, this is negative, this is positive, right? Sum those and set that equal to each other. Okay, you'll have an equation. That's good. But what we want to do is skip ahead to doing the sum of the torque. Okay? Because remember, for Newton's laws problems, initially we just summed forces, and we wondered if the sum of the forces is equal to 0 or sum of the forces is equal to ma. And now, since there is rotation, you should also be thinking about torque, right? Sum the torques is equal to 0. Sum the torques, is it equal to an acceleration, angular acceleration? Okay. In this case, there is a net torque that's causing an angular acceleration of the disk, right? Now, remember, when you're calculating torque, unlike forces, which are very apparent which way they point, right? Tension's down, mg's down, normal force is up, right? It's very apparent, and nobody's going to disagree with this, really, right? But when it comes to torque, it does matter where you pick to find torque, okay? You can find torque about this point right here, this right here, right? If I pick this point, I can say, okay, all these forces have some distance to that point, right? So from this point, the normal force is this distance away. From this point, this force is this distance away, right? So each force, depending on where you pick to do torque, has a certain distance from that point. Okay, so torque it's a little bit harder to deal with because of the subjectivity of where you pick to sum your torques, right? So the general idea is you want to pick a point that minimizes the number of torques you have in your equation. Okay, that's generally the idea. But also, you don't want to eliminate the thing that you're trying to solve for, right? For instance, if I pick this point, right, as my place to calculate torque, this force that I'm trying to solve for is not going to appear in the torque equation, right? Because there is no distance to this tension from this point, right? Is that clear? So you kind of see that, right? So if you have a point like this and you say that's the point I'm going to calculate torque about, well, this force has no distance from that point, so then it won't appear in the torque, right? So you don't want to eliminate the thing that you're trying to solve for, right? So that's one thing. The other thing is also you want to try to get rid of the things that you don't care about. You don't care about the normal force, nobody asked for it, right? So this point right here is a good point to choose to calculate torque because there's no torque by the normal force, there's no torque by the weight, the only torque is produced by the tension force here, okay? And notice that, so if you pick that point, what do we do for R cross F, right? Remember that torque is equal to R cross F. You have to do the right-hand rule, right? So here's our R, right? So here's our R vector, right? These are all vectors, of course, but this is our R, right? So we do R cross F. Your thumb points towards you, right? Up from this page, right? You go R cross F, thumb points up, right? So hopefully you're practicing your right-hand rule. R cross F, right? Thumb up, thumb towards you. So that's the direction of the torque. Notice that R and the force are perpendicular to each other, right? And then by the definition of torque, the magnitude of torque is the magnitude of R times the magnitude of F, sine of the angle between them. If the angle between them is 90 degrees, sine becomes 1, right? So that simplifies into just the distance times the force, like normal arithmetic multiplication, right? So what that means is when you try to sum up the torques, the torque is the tension times that distance, which is the radius of the disk. Okay, so when I use little r, I mean any distance, right? When I use big R in this case, what I mean is the radius of this particular disk, right? So that's the torque, that's the only torque that's on the disk about the center point, right? So that has to equal, that's torque, has to equal the moment of inertia times alpha, right? Angular acceleration. So that allows you to solve for angular acceleration is the tension times R divided by I. Okay, still kind of making progress, right? We at least found the ways that acceleration and linear acceleration is related to tension. We found that the angular acceleration is also related to tension. So we need to kind of put all of this together, right? And figure out a way that linear acceleration and angular acceleration are related, right? So if you look at this, as the disk accelerates, then the box also accelerates, and there has to be a relationship between the two, right? That they're not independent of each other. As this is accelerating, this is not independently accelerating. It's somehow they're connected, right, of course. So as this accelerates downward, it has an effect on the disk, right? The amount that the disk is accelerating, alpha and A, are related to each other, right? Because they're connected together. So how are they related to each other? We go to our definitions of our angular velocity, angular acceleration. Angular velocity, remember, was omega cross r, right? Angular velocity, take the cross product with the distance, you get tangential velocity, right? So this, the acceleration here is kind of like a tangential acceleration to the disk, right? So if we look at acceleration, tangential acceleration, that's equal to alpha cross r. Okay, so angular acceleration, remember these have directions, right? So the angular position had a direction, angular velocity has a direction, angular acceleration has a direction, right? So that vector, take the cross product with r, and that will give you the direction of the tangential equivalence, right? Acceleration, velocity. If they're perpendicular to each other, right? In this case, it is perpendicular, because as the disk accelerates, its angular acceleration is going to point up at you, okay? So the angular acceleration is up at you, and the r, the distance to this point, is also perpendicular. So these two are perpendicular to each other. So that means sine is 1, which allows us to write a is equal to alpha times r, okay? That's important because now we have a connection between everything else, right? Because now we can solve this using kind of a combination of these three, right? So we have this, they have the tension equation, we have the alpha, and we have a relationship between how the two different accelerations are related to each other, right? So there are three unknowns here, right? A is unknown, alpha is unknown, tension is unknown, but we have three equations. So we can mix them together to solve for the different variables that we're asked to find, right? So if you mix these equations together, do a bit of algebra, I'm going to show you what you should get. I trust you can do the algebra, so I'm not going to go through step by step with that. I just want you to kind of see the setup for solving problems like this. So if you mix these equations together using a bit of algebra, you should get that the tension is equal to mg divided by 1 plus mr squared divided by the moment of inertia. Okay, that's what you should get for tension. Notice we're doing all of this in variable form, right? So no numbers, which is good. We're going more and more to the direction of being abstract, right? So which is important, particularly for physics 2. So alpha is going to be mg times r divided by the moment of inertia plus mr squared. Okay, one more, we need A is equal to mg r squared divided by I plus mr squared. Okay, so you can get all three of these by doing a bit of algebra. Using these three relationships, you can combine them in such a way that you can isolate these terms, right? In terms of properties of the system, the mass of the box, the radius of the disk, the moment of inertia of the disk, and so on, right? Okay, questions about this? Anything we've talked about, the setup, any kind of step that is a little confusing?
We have some questions going back to the formulas. Could you reiterate where the acceleration is equal to angular acceleration times radius?
Yeah. So where this is, so it's an extension of this, right? So remember, let's pull up the notes when we talked about the definition. Yeah, so going back to our definition of angular velocity, right? Even before that, maybe just to remind ourselves, remember, even before we talked about angular velocity, we're talking about an angular position, right? Going around a circle. you have an angle, right? So remember that angle, if you say this angle is 30 degrees, it's not clear by saying just 30 degrees. Did you go from A to B or B to A? Right? So just saying 30 degrees doesn't really help if you're trying to come up with a direction that you traveled, right? So if you're saying I went from A to B, then 30 degrees has to also account for that, right? So that's why angular position, you need some sort of direction, otherwise it's not clear, are you going clockwise or counterclockwise? And clockwise and counterclockwise is not very precise, okay? So to make it more precise, what we do is do this, where we give the angle a direction, and yeah, it seems a little odd when you do that at first, but you kind of get used to it, right? So the angle has a direction. So when you say I'm going counterclockwise, the direction of angular position is up, perpendicular to that plane of your circle, okay? So, and the way you relate all these directions is using the right-hand rule. So if you do if you do theta cross r, right, with your right-hand rule, you should get S, the direction of travel, right? The steps you're taking is in this direction, right? So as an extension of that, then we talked about, okay, we know what an angular position is. What is an angular velocity? Well, it's a derivative of angular position. And angular velocity also needs a direction, right? If your record player is spinning clockwise versus counterclockwise, right, you need to know that. So how do we relate angular velocity and give it a direction? We follow that same direction. So if your disk is on the xy plane, then the direction of angular velocity is perpendicular to that, right? And that's our fancier way of saying counterclockwise, right? Looking from this top view, right? So then how do you relate the tangential velocity, right? The disk is spinning and that surface of the disk has a velocity. That little piece of it has a linear velocity for a very, very small, like think about 0.00001 seconds. For a very, very small period of time, that little segment of the disk is going in a straight line, right? In the grand scheme of things, it's going in a circle, but for a moment, right, it's like taking a little step forward. And so that tangential velocity is related to angular velocity, again, using the cross product. As you can see, the cross product is really important, right? That's why we spend a lot of time with the cross product, because that's how you make sense of all these directions, right? Because the directions are not very intuitive, right? Because it's not like when you said a velocity, if you look at a bird flying and you say, where's the velocity? You can visualize the velocity vector of a bird, right? Just because you see how it's going. It's not obvious how these directions kind of go, and so we use the right-hand rule, we use the cross product to help us figure out what these directions are, right, and keep them consistent. So omega cross r gives you velocity, right, tangential velocity. So practice that, right? So here's the omega vector, here's r, right? If you do your right-hand rule, do you get the velocity vector pointing like this, the tangential velocity, right? Is it the direction of your thumb? Check that, right? So omega cross r is tangential velocity, and notice there is an acceleration. I didn't say what the cross product equivalent of acceleration is. Now we need to really think about that, so that's why we're dealing with it here. And we're saying, okay, just like tangential velocity, tangential acceleration or linear acceleration is alpha cross r, okay? The direction of angular acceleration crossed with r gives you the tangential acceleration. If alpha and r are perpendicular, right? In a lot of cases, that's the situation, because if you look at this, for instance, right? In this case, omega and r are perpendicular to each other. So the nice thing is the cross product simplifies to a simple multiplication. Okay? Because why? Why? Because in the definition of the magnitude of a cross product is the magnitude of the two vectors in sine theta. So if the sine of theta, the angle is 90 degrees, then sine is 1. And then that's what's happening here, where the angle between them is 90 degrees. So then you can say sine of 90 degrees is 1. So then it's just alpha times r. So it simplifies only when alpha and r are perpendicular to each other, right? And in this case, it is the case, right? Hopefully that helps. Ask more questions if that's the cross product stuff is not clear. How are we doing? Good? Yeah.
Yeah. We had a question asking if they would be able to do this question if it was not perpendicular. I'm assuming they're talking about the torque, probably, or the force.
Yeah, maybe the person asking the question could specify what you mean by not perpendicular, because do you mean the forces being not perpendicular, or do you mean if the acceleration is not perpendicular to r? Which one do you mean?
I think they mean if the torque isn't like perfectly perpendicular to the radius.
Oh, okay, yeah. So if you have a case, yeah, that's a good question. So if you have a case, right, so let's take this example and maybe think about, how would you kind of set this up? Let's say, yeah, let's take this and add a force to it, right? So let's say we have this disk, right? And we know about the tension, right? So this is this way, right? And that makes the R that, right? So this is the tension, and that's your R, right? Remember, you start with where you want to calculate torque about. That's subjective. That's not predefined, right? Like you have to make a decision there where you want to calculate torque. That's your call. So if you make a call that this is the center and this is what you want to calculate torque about, then R is from that point, go find where the force is acting, right? So the force is acting at this point, right? And then pulling down. So go from here to here, right? If I had a force kind of like that, Kyle, make up a variable name. H, okay. So if we say that's vector H something, right, some sort of force that's acting like this, it's the same deal. You have to start from where you have your torque calculation, where you're trying to calculate torque about, and go find where that force is, right? That's your R, right? And now this is not perpendicular to each other, right? So now look at that, right? So you start, and there is an angle between them now, right? R cross F, right? So when you're calculating torque, you have R cross F. And remember, zero angle means that R and F are both in the same direction like this. This means theta is equal to 0, right? So you measure from this, and then on top of that, if the force is changing direction, let's say that's your R, then you measure from this 0 point. That's your angle, right? So in this case, this is how we measure the angle. The cross product is still valid for this, right? And you can also still find the magnitude of torque. If you say, what is R, the magnitude of R, what is the force? Magnitude, oh, actually, let's not write F, let's say H, right? So what's R in that case? What's H? And then sine of the angle between them, right? If you know the angle, then you should be able to find what the magnitude is. Now, the direction comes from the right-hand rule, and you can still use your right-hand rule on these, right? That's why I like the curling one a little bit better, because it's a little bit more, I don't know, flexible, I think, because you can go R along the first vector, right, is R, 4 fingers along R, and I curl towards the force and my thumb points down, right? And that's still valid. So you can still use the right hand rule to figure out the direction of torque. You have the direction of torque using the right hand rule, you have the magnitude of torque using this, right? And then that is the definition of the vector, because you know magnitude, you know the direction, you're done, right? Does that make sense, right? So yeah, so you can have more complex situations. That's reality, right? When you go into the real world, you're going to have very, very complicated situations to deal with. When we start off with simpler conditions, right? But that doesn't mean get only focused on situations like this, expecting this is all you're going to see, right? That's not all you're going to see. We start off with stuff like this because it just makes it easier to get started. The cross product is hard, right, to learn at first. So then, but you are able to do this too, right, if this is the situation you're given. That help, hopefully, with that? Ask more questions if that's not clear.
They followed up with, in this example, would you solve for torque twice?
Would you solve for torque twice? Yeah, good question. So if you go back here, right, now instead of 3 forces, if you introduce a 4th force, and you're still sticking to the center as the point you're calculating torque about, the normal force and the weight still don't contribute, the tension still contributes, and that force that appears here will contribute, right? So yes, when you're doing Newton's second law for rotation, when you're doing the torque calculation, you will have another torque in here, right? And then that is going to equal I times alpha, right? So notice the similarities. This is should be very familiar to you from the Newton's laws for linear motion, right? When you did sum of the forces, you included as many external forces as there were, right? In cases like this, there's tension, there's weight, you put both of them down, right? Same thing for torque. It's not that you're going to have only one torque. You might have 18 different torques, right? That's applied to a certain object. There's no limit, right? It can be multiple forces multiple torques and multiple forces that are acting on an object, right? So you got to be paying attention to that. And with the torque, it's a little bit more complicated to deal with torque, right? Because for one thing, it requires a decision on what point to apply torque about, calculate torque about. Unlike the case of the forces, right? The forces, you don't really have to make a decision, oh, do I count that or not count that? Once they know those are external forces, they all go into Newton's second law, right? You don't have a choice in the matter, right? But with torque, technically they're in there, just they're zero, right? So technically the weight, the torque due to the weight is in here. It just happens to be zero, if you want to consider it that way. But yeah, there's a little bit more subtlety to calculating torque, right? Other questions?
Is this going to be on the midterm?
Yes, so we will cover everything up through what's on the homework. So on the homework, you don't have angular acceleration situations, right? So yes, in the sense the torque calculations will be there, but we'll stop at essentially static equilibrium when it comes to torque, right? Because that's what's covered in the homework. For instance, if there's something balancing, right? You're trying to balance something like the meter stick we looked at the demo, right? Where you balance the forces, you balance the torques, and the net result is it doesn't accelerate. That's fair game. When there's acceleration, as you can see, it gets a little bit more complicated. We'll deal with that later. I know it's a quick class, right? 5 weeks, and we have to learn all this stuff. So we're trying to take it as slow as possible, right? So that you have the time to digest this. For midterm 2, definitely spend some time with torque, right? So this part of it, that torque is equal to an acceleration, we'll deal with that later. But the cases where torque is equal to 0, right? Sum of the torque is equal to 0. That's something you should be familiar with. And you should be familiar with the cross product, right? And how to find the magnitude of the cross product and things like that. Okay, keep asking questions, and I'm going to go and talk about linear momentum. And yeah, so keep asking questions. If torque is not clear, fair game to ask that too. Anything while we... Oh, this one, this one right here, it's going to take a few steps to get to the algebra. It's not the most interesting thing like to cover during a lecture because it just takes up a bunch of time and it's a lot of algebra. Try to do this yourself. If you cannot get to this, post what you get so far and we'll work through it on Ed Discussion, right? So as you can see, I kind of emphasize a lot about starting the problem, free body diagrams, applying Newton's laws. That's 80% of the time should be spent there, right? There is some algebra to get to the end, right? That's less important because I trust you can do algebra, right? What's new for most of you, all of you maybe, is doing all of this, right? Free body diagrams, applying Newton's laws, right? So spend a lot more time there. And the algebra is honestly not as bad as it looks, right? It's just a matter of taking this equation, putting it in there, taking this equation, putting it in the alpha that now appears here, and cleaning up the algebra, right? It just takes a lot of time from like lectures, so when I do it, students get kind of bored. So I try not to do that because, yeah, it gets a little tedious and you're just watching me do algebra, which is not that entertaining. But if you cannot get to these, this is what the end result looks like. If try to do the algebra yourself and post what you have. If you get stuck, post it on Ed Discussion, and we're happy to help kind of get you to the end, right? So if you need some help with that. Okay, so let's talk more about momentum. Okay, so we've already talked about momentum when we talked about Newton's second law, right? Actually, it is about momentum, right? Because what it's saying is that the net force, right, that's on an object causes momentum to change with time. Okay? And earlier we defined what momentum was. Linear momentum is P is equal to mass times velocity, right? So this is what we're calling linear momentum. Okay. What we're going to do here is rearrange some of these terms a little bit, right? So I'm going to move the time over to the left-hand side, and I'm going to write that the net force times dt is equal to dp. Okay. All I'm just doing is moving some terms around, and I'm going to give this left-hand side a new name. I'm going to call that impulse. Okay. And the symbol we're going to use is J. Okay. It's not that important that you create this new thing, right? Because this is the fundamental idea, Newton's second law. And if all you had was that, you're perfectly fine. This is for convenience that we're doing this, right? Because what we're going to say is that an impulse, that is a vector, it has a certain direction, causes momentum to change, right? Not over time, but just change. Okay, so it's convenient if all you care about is a change in momentum, okay, and the time part you kind of shove to the left-hand side, right, and you kind of put all of that time and force stuff on the left-hand side. So for some problems, this is convenient to think of it this way. It is not critical that you do this, okay. In the case of an airbag, this is kind of helpful, right? To kind of think of it this way. When you have a car, right, it's traveling, it has a certain linear momentum. It has a certain mass, it has a certain velocity, right? When the car comes to a stop, right, it has no linear momentum, right, because its velocity is 0, right, or almost 0. Same thing for you. You're in the car, you have mass, you're traveling at a certain velocity, right, relative to the ground, so you have some momentum, right? So if you come to a stop, there's a change in momentum, right? If you're in the car, right? Hopefully not, right? This is hypothetical. If somebody is in an accident, right, in a car, and their momentum changes, right, it has to change. You have a certain momentum to start with, and then now it's essentially 0, so it has changed by some amount. How you go about it, right, can be different depending on if you have an airbag or not, right? Because the amount of momentum that's changed is caused by impulse. What an impulse is a force over some time period, right? So in our case of the airbag, you have a choice in the matter, right, in some ways. You could have a very large force applied over a very small time to produce a certain impulse that actually changes your momentum. That's what happens in the case of not having an airbag, right? If you run up against the dashboard of your car, there's a huge force over a small fraction of time. So in the video we kind of saw that where for a very, very tiny period of time, the crash test dummy is getting a huge force applied. Or what you can do is say, well, what if I reduce the force but increase the time, right? I have a lot of time to work with, and that's what the airbag is doing, right? You still have the same impulse being applied to change the same momentum, right? If you compare apples to apples, a person traveling at 65 miles an hour that comes to a stop because of an accident, right, because of a collision, because that person, right, if you compare apples to apples, let's say the same mass, same change in velocity, you have the same change in momentum, a certain impulse is necessary to change the momentum, but you have a choice, right? Which one do you want? You want the large force over a short period of time, or you want the small force over a longer period of time? So the airbag prolongs that collision with the dashboard, right, or the front of the car. It adds more time, and that's enough to reduce the force, right? You don't need such a force acting on you to change your momentum now, because you can provide the same impulse with a longer duration of time, right? So moving the time to the left-hand side helps you kind of see this a little bit better than kind of dealing with Newton's second law outright. It's still in there, right? But moving it around helps you kind of think about, oh, wait a second, if I wanted to change momentum, how do I go change momentum? Well, I need to apply a force over a time period, right? In the case of the airbag, well, I want a large time period and a small force, right? I don't want a large force on my face, right? And that's not a good thing. Okay, let's do a problem, get a feel for how to use these terms. Okay, so we're talking about car, collision, safety, right? So let's say there's a car, has a certain mass, 1,500 kilograms. It's traveling initially, the initial velocity is negative 15 meters per second in the I-hat direction. Let's say my coordinate system is x to the right, y up, standard coordinate system, right? It's traveling initially in the negative direction, I-hat, and then final velocity after the collision is 2.6 meters per second, again, I-hat, positive now. The collision happens over a time period of 0.15 seconds. Okay. What is the impulse? Okay, what impulse did the car experience during this collision? All right, so take a look at that. I'm going to shift over here. There you go. So that way you have the definition of what impulse is. Try to think about it. Throw some ideas into ed discussion of how you might approach this, or if you want to post your work, welcome to do that. There are thoughts on how to solve this? Not yet? Okay. What are some thoughts? How do we do this? Before you do it, what's a strategy? Depending on what we have here, what can we do to find impulse? What information is provided? Right? And think also like, okay, velocity is of course provided, but what does that mean? If we know velocity, what else can we figure out?
You should find the acceleration by using the velocities to find the force, then use the time interval to find impulse.
Right, so you could do this where you have a change in velocity, you have a change in time, right? That's an acceleration. We know accelerations are caused by a net force. You can find the force. If you know the force, you can multiply by the time period to get impulse, right? Force times time is impulse. So that's one strategy. Good. You can try that, right? So notice now you will have a multiple ways of solving problems, right? Now, the more you go through physics, you have more tools. That means you're not just forced to use kinematics or forced to use Newton's second law. You can start using different techniques. And later in the class, we're going to talk about energy. That's going to introduce another set of tools for you to use, right? So far we're kind of more or less centered on this idea, right? Newton's second law. But yeah, you're getting multiple ways to solve it. So that's one way to do it. What else can you do? There's another way to do this.
We have calculate final and initial momentum and
Good.
the differences in impulse.
Yeah, exactly. So you can find the momentum initially, right? So momentum initially is the initial velocity times the mass. You can find the final momentum, final velocity times the mass, right? You can find the change in momentum. And if you know the change in momentum, then you know impulse, even before you do anything with forces. You don't even need the force anymore, right? You can just tell what the impulse was just because you know the change in momentum. So try it in both ways. Let me try, I'm going to do it in one way, but try both ways if you want to do it the other way. I'm going to do it through using a change in momentum, just to give us a little bit of practice with this. Right, a change is final minus initial, right? So always final minus initial. They're vectors, be careful, right? So when we're talking about the final velocity, what is the final velocity? Well, it's 2.6 meters per second, right? Velocity, mass times velocity, doesn't matter the order really. 1,500 kilograms, right? And what direction is it? It's in the I hat direction, right? We want to subtract that by the velocity initial is also negative, so watch the signs there, meters per second, right? Times, again, 1,500 kilograms, again in the I hat direction, okay? And if you did that, you should get a positive 2.64 times 10 to the 4 kilograms meters divided by seconds. Momentum and impulse, they have kind of odd units like this, but kilograms meters per second, and also in the I hat direction. Okay, so imagine the car, right, that the car was initially traveling to the left, right? It was going in the negative x direction, right? So v initial. And then after the collision, it was going the opposite direction, right? It was going this way, v final, right? So initially it was traveling to the left, let's say, and then after the collision it's going to the right. What does the impulse say? The impulse says it's pointing to the right, right? So that's the direction of the impulse. If a car was coming, let's say it collides with the wall, car is coming, it collides with the wall, the impulse that the wall puts on the car is that way, right, to the right. And that's what the impulse calculation is telling you, right? It's saying there was an impulse to the right, that's what made this momentum change, right? It is a change in momentum. And when you change momentum, that change is in a certain direction, and it's to the right, in the positive direction was the change. It took a negative number and made it positive, right? Okay, so given this, we can still talk about a force, right? So if you calculate the acceleration and found the force already, then that's good. But now, if you have it, we can make a comparison, right? So let's compare what you got that way to what you can get using impulse, right? Knowing the impulse, you can now get the force, right? So you have a force is, so impulse is force times some period of time, right? So it's technically a little bit of impulse, right? So ideally you're integrating this, but if you want to say impulse is force times time, you can do that, right? So the integral allows you to deal with more intricate situations, but in this case, we have an impulse, we have a net force, right? So the net force acting on this car, taking the impulse and dividing it by the time, the delta t, 2.64 times 10 to the 4 kilograms meters per second. I hat, right, if we want to kind of keep track of the directions. And then we'll take the duration, 1.5 seconds, right? We'll give you 1.76 times 10 to the 5 newtons in the I hat direction. All right. If you just want the magnitude, you don't have to worry about the I hats, but this helps us keep track of direction, right? So if you just take the impulse and divide it by time, you will get a force. So if you did it the other way with acceleration, you should get the same number here as well. How are we doing?
We have a question about units.
Okay.
They're just asking if it could be Newton seconds.
Sorry, what about Newton seconds?
If the units, they're just asking if they could use, for the impulse be Newton seconds.
Oh, yeah, so remember newtons are derived units, right? So if we kind of write F equals ma, so F equals ma, the units of that, what are the units of that? Newtons is equal to kilograms meters per second squared, right? So that's the F equals ma is telling you newtons are actually these, right? So when we say a newton, we mean a kilogram times meters divided by second squared, right? So if you have this situation where you have a force times time, what you're saying is, okay, a newton times seconds, and that's equal to kilograms meters, right? And there was a 1 over second squared and a seconds being multiplied, and then you have seconds canceling, and so what you have is kilograms meters per second there, which is what we had before, right, for impulse and momentum, right? Does that make sense? So yeah, you could list it, excuse me, you can list it as Newton seconds, but Try not to do that because you'll see later why that is. So yeah, oftentimes just list momentum this way, kilograms, meters per second. It is kind of strange because sometimes we do use kind of derived units that have names to them, even though it's really this, right? We could be writing this, but it's a little tedious to keep writing kilograms, meters per second squared every time you have to write a force down. So that's why we just write newtons. But sometimes there's no name for these units, right? It's, yeah, one day when you're famous, you've done lots of science, maybe they'll name it after you. So until then, we just have to deal with kilograms, meters per second. Good?
Yeah.
All right. All right, let's try another problem. Let's do an Instapol, give you a little bit more practice with momentum. Switching to the computer here. Okay, so let's send this your way. Okay, so let's take a look at this. We'll be back in a minute and a half. Okay, let's take a look at what we have. Okay, so still waiting on a few more responses here. Put in your best guess. Remember, you can always change your mind afterwards. You're not locked into your answer, but it's important to try out the question, see what you think, right? So that making an attempt is a very important part of the learning process. So make your call here. Okay, let's see what we have so far coming in. Okay, we have the change in magnitude of the momentum is the same for both. The popular answer, then we have the car and the truck, almost about the same, right? So there's a question on that discussion about the truck being more massive. Yeah, you can assume, right? So it doesn't say in the problem itself, but you can assume that the truck is more massive than the car is, right? So they're traveling at the same speed. If the truck has more mass, it has more momentum, right? They collide, they stick together. Which car experiences a larger change in momentum? Okay, So let's go to our notes and see if we can draw a picture and figure this out. If we have the truck, right, doesn't have to be too detailed, right, in terms of the diagram. This could be the truck. And this could be the car, right? So that's your car about to collide with each other. We are told that they have the same speed, right? They make a head-on collision, they have the same speed. Their velocity vectors will point in opposite directions, but the magnitude is the same, right? The speed is the same. The truck is more massive, right? So the truck has more momentum, right? We agree that the truck has more momentum to begin with than the car. They collide, they stick together. What's the change in momentum is the question, right? So how do you change momentum? All right, going back to our discussion of linear momentum and impulse, you change momentum by having an impulse, right? So the truck and the car, their momentum changed, right? We know that it changed as a result of the collision. How do you make a change in the momentum? You have an impulse. You have a force over a certain time period, right? So let's take them one at a time. Let's talk about the time period. If you look at this collision between the car and the truck, is one more in contact with than the other, right? Is the truck in contact with the car for a longer, shorter period of time than the car is in contact with the truck when there's a collision? Yeah, it's the same, right? So it doesn't have to be a car and a truck. They take a tennis ball and throw it against the wall, right? It's kind of like that. If there's a collision between two objects, they're in contact with each other the same amount of time, right? The car in contact with the truck and the truck in contact with the car. The collision process takes the same for both things, right? So in terms of impulse, the time period isn't different, right? So let's talk about the force, right? If this car pushes on the truck by a certain force, right? Let's say the force that the car applies on the truck, right? And compare that to the force that the truck applies on the car. We know there's a connection between these two forces, right? What's the connection? How are they related to each other? Throw it in that discussion. Let Kyle and Jericho know. Do we have any idea how these two are related to each other? I'm sorry?
Is it the same speed?
Oh yeah, the collision's happening, they start off with the same speed. Yeah. They're equal and opposite, right? Newton's third law, right? It's a very important one, not prominent in terms of solving problems as Newton's second law. Newton's second law comes up all the time, right? But it's really, really important. There's so much information there that is really handy, right? Don't forget Newton's third law, right? If a car applies a force on the truck applies the same force on the car, opposite directions, right? The magnitude is the same. So if you have a collision like this and you have a change in momentum, that's what we're trying to calculate, the time period's the same. The force on each other is the same. So each of the objects will experience the same change in momentum, right? Now, the truck, if it's very massive, is not going to be too bothered by the car colliding with it, right? So that's the kind of the subtlety of it, right? Is that if the truck is actually traveling that way, collides with the car, its momentum and the car's momentum will change by the same amount, but the truck, because it has more momentum, will maybe be carried more to the right. Right? In reality, if they're not going to collide and just stop, right? They will, if they're coming at each other, they collide, and the truck will probably carry the car to the right, and that's probably what you're kind of thinking about in terms of, wait a second, the truck is more massive, so what gives? That's what gives, right? How are we doing? Good? Okay. Let's go to our notes, carry forward with the discussion. Let's think about momentum a little bit more. Okay, so Newton's second law says that if you have a net force, it changes the momentum of that object over time. What if there is no net force on that object? There could be situations like that. That means the change in momentum over time is zero. If a derivative over time is zero, what does that mean? That means that the momentum is constant, right? If you have an object, it has no net force on it, or you have a collection of objects that have no net force on it, then the momentum is constant, okay? So another way to say this is that the initial momentum is equal to the final momentum. Okay, this is the conservation of momentum. Okay, conservation as kind of preserve, right? So the initial momentum is preserved, right? Before and after, they're the same. Okay. So for this to be true, there are two requirements. Okay. One, we have already stated, right? The net external force on the system must be zero, right? We've already stated that, right? That's how we got here in the first place, right? It can't have a net external force on the system. If it did, it changes momentum. That's Newton's second law. The second one is that the mass of the system must be constant. Okay, so if you're trying to play pool, billiards, right, and you're looking at the momentum of all the balls before and after the collision or whatever it is, you shouldn't throw more balls into the pool table. You shouldn't take balls out of the pool table, right, if that's your system. Okay, it may seem obvious, but you shouldn't change mass, right? If you're focused on a certain system, that system should maintain its certain mass, okay? Because if you have mass coming in and out of the system, then this won't hold. This will, right? This is more general. When you say a net force causes momentum to change with time, that's more general. But when you're coming up with a specific situation where you say net forces are equal to zero, and you come up with momentum's conserved, for momentum to be conserved, there should be some requirements, right? It's not generally true. Okay, so just like with F equals ma, notice this is a vector equation, right? So even though you write one equation, you know now that whenever you see a vector equation like this, it's actually three equations, right? So this equation here can be written as the momentum in the x direction initial is equal to the momentum in the x direction final. That's one equation. Momentum in the y direction initial is equal to the momentum in the y direction final. Momentum in the z direction initial is equal to the momentum in the z direction final. So there's three equations hiding in here, right? This is the compact form of writing it. Nice, right? Because it looks pretty, it's very easy to write down. However, it's a little deceptive because all of these are actually what it's actually saying. So in practice, when you're solving problems, you often are actually using this, right? This is what goes on T-shirts, right? But this is what is actually used in practice, right? When you're trying to solve a problem, you want to actually look at the X, Y, Z components, right? Questions so far?
Shouldn't V also be constant so momentum doesn't change?
Should V also be constant? I see. No, well, yeah, if we're talking about individual particles colliding, for instance, you could have a case where a certain particle starts off at rest, but now has a velocity after the collision, right? So we're looking at the system as a whole. So no, it's not necessary for the velocity to be constant, right, for the individual particles. It's that the momentum of the system as a whole before has to equal the momentum of the system after. So long as you have the same stuff on the table, let's say, right, the pool table, the same amount of balls that you're playing pool with, then yeah, the requirement isn't on velocity, the requirement is on momentum as a whole, right? Okay, let's take a look at this demo video, gets you thinking about collisions in 2D. So this is a air table, and what you're going to see is not just a collision in one dimension, but you can see collisions that are happening in 2 dimensions. And that's going to help you start thinking about, oh, okay, how do I deal with momentum when there's multiple dimensions involved? So here's a demo. We'll come back afterwards. So in this demo, we're going to look at collisions, specifically in 2 dimensions. So we have this table that has little holes where air can get through. So it's an air table. When I turn it on, there'll be some air flowing through each of these little holes. And so that produces a surface that has little friction, so then we can deal with collisions that way with minimal friction. So we have this table. We can use that to consider collisions in more than 1 dimension, so 2 dimensions in this case. You can think of this as, say, the y dimension. That corner could be the origin, so positive y, positive x. So you have a y and an x, and you can have initial collisions, initial velocities in 2 different directions and see what happens. So to start, let's think about a collision in just 1 dimension, just in x. So when I have these 2 objects coming at each other, just traveling in the x direction, this one has a velocity this way, this one has a velocity that way, and so when I push it and let go, that 2 objects, they have a momentum, right? As a system, they have some momentum, and after the collision, they should still maintain that same momentum, so conservation of momentum. When the collision happens in just 1 dimension, in the x direction, then that's all you need to worry about. What's the velocity in the x direction in each case? But now what we're going to do is do this in 2 dimensions. So let's say this object only has an x velocity, so negative x, for instance. This has a velocity this way, and now this object will have a velocity both in x and in y. So let's say if they happen to collide right here, right? So let's say we're looking at 2 dimensions now. So as you can see, now you have to consider momentum both in the x direction and in the y direction. So what's the initial momentum of these objects? So this one has a momentum in the x direction, so that has a certain momentum. this has a momentum both in the x direction and the y direction. So what we have to do to figure out what happens after the collision, how they come off the collision, is to figure out, well, we have some initial momentum in the x direction, we have some momentum in the y direction, and afterwards, after that collision, those two momenta have to be the same. The x component and the y component still has to be the same. So that's what you see in two-dimensional collisions. After the collision, it still has the same momentum, but not just momentum in general, specifically momentum in x and y. So you can think of this in real life. Where would you might see something like this? It could be a collision of two cars, for instance, on the road. What happens if two cars going in two different directions collide? We can start to understand what will happen afterwards. So that's collisions in more than one dimension, two dimensions in this case. Okay, so let's take a look at collision actually at maybe a T-junction on the road, where you will see collisions in two dimensions now, right? It's not just head-on collisions. Okay, so a collision at an intersection. We draw a road like this. Probably seen a road like this, right? So something that looks like a T, right? And it could be a car traveling here to the right. It's 1,500 kilograms, 25 meters per second in the I hat direction is its velocity. And we also have another car, 2,000 kilograms, and it's traveling up 20 meters per second in the J hat direction. Okay, and you can see at some point in time they will meet right here. They will collide, right? There'll be a collision. They'll stick together and they will travel collectively in a certain direction like this. It will have a final velocity. We have a certain angle to the final velocity, right? And our objective is to find out what this final velocity is, its magnitude, its direction. After the collision, where is this pile of cars, right? So the cars that have collided together, that pile of the two cars, where is it actually traveling to, right? So it's traveling in a certain direction. Based on the initial, can we figure out what happens at the end, right? So a couple of times now we've talked about collisions that collide and stick together. Not all collisions are like that. Some collisions, the things will collide and bounce off, right? So there are different outcomes. So colliding and sticking together is just one of the outcomes, and so we'll look at one case, and that's the case where they stick together. Let's also keep in mind of a coordinate system. Let's use the standard one. There's no reason to rotate it, right? So the standard one's perfectly fine. And we want to think about how to approach this, right? So do you want to deal with Newton's second law outright? Not really. Why not? Well, to do that, you'd have to figure out the forces involved, right? Because if you're trying to find the final velocity, there is an acceleration caused by a net force. So this one is having a certain velocity. It has a final velocity that's different. That means it accelerated. Why did it accelerate? It had a net force. What is the net force? That's not easy to find, right? So when you're talking about collisions, oftentimes you don't want to deal with F equals ma, because not that it doesn't work, it's really complicated, right? To figure out what the forces are. The forces are really complicated in the sense that when a collision's happening, the direction of the forces involved are constantly changing. The magnitude's changing, the direction's changing, right? The cars are getting crumpled up. So the forces involved are actually quite complex. So not a good idea to use F equals ma in the case of a collision. So if you ever see problems involving collisions in physics, right away start thinking about momentum, right? And particularly the conservation of momentum, okay? Because if we treat both the cars as a system, right, then there are no external forces that we need to worry about, right? Because everything that's happening as part of the collision is part of the system. Because when we're considering the two cars as a collective, then anything internal, any kind of pushing and pulling that they do to each other is internal to the system, and therefore is not going to be counted here, right? There is no net force if we consider both cars together. So that's why we're going to do that. Now, if you say, well, I want to focus on this car as a system, then it does have an external force, right? Which is coming from this, right? So if there is an external force or if there isn't, right, this is how you define the system. If you define the system to be this car, that's your system, right? Well, of course, this car that pushes on it is an external force, and you have to include that, right? So pick your system to your advantage, right? You're allowed to pick the system, and the biggest system you can pick is the universe, right? The universe itself you can consider as a system, right? As far as you know, that's as far as it goes, right? So that's the biggest thing you can think in terms of system. That's everything, right? So, but any subset of that works, right? So my pen could be a system, this car could be a system, both the cars could be a system, right? So it's up to you. But choose the system in such a way that it makes your calculations easier, right? So by choosing the system to be the two cars, we can say that momentum's conserved. Momentum initially is equal to the momentum final. Okay? Again, like I said, in practice what you're doing is this, right? You can say this all day long, but really what you need to be doing is this, right? Setting the momentum in the x direction, initial and final, to each other. Same thing for the y, right? So let's go ahead and do that. I'm going to split my page and do x's on the left, right? So what I'm going to do is x here, and I'll do y here, right? And initially what I'm going to do is sum up all the momentum in the x direction initially. It is a sum. You do have to, because there could be multiple objects in your system, you do want to kind of add them as vectors together, right? So you come here and say, okay, I need all the momentum in the x direction initially. This car doesn't contribute anything to the x direction, only this does, right? So then we add that to this, so we say, okay, the initial momentum in the x direction is the 1,500 kilogram car going at 25 meters per second. And it's positive, right, because it's going in the positive x direction. Okay, so we keep that. That's our initial. We sum up all the momentum in the x direction final. Okay. After the collision, they stick together and they travel in this direction, right? So that collective thing, that object, has a momentum in the x direction and a momentum in the y direction, right? It has a bit of both, so we need to solve for that. You have to do your SOHCAHTOA, right? Because this is a vector, right? So you're now familiar, this is a vector. When you have a vector, you want to break it up into components. The vector itself is the hypotenuse of a right triangle. You need two more sides to your right triangle. Follow x and y. You come to the bottom starting point of that vector. Follow the x direction. Go along the y direction. Form your right triangle, right? This is not going to help you find the components of your vector. For the final momentum, when they stick together, you add up all their masses, right? 3,500 kilograms. The x component of the velocity is Vf, the final magnitude of the velocity, cosine of that angle. right? So when you have this, what is this side of this right triangle? That's the cosine part, right? VF, cosine of theta, adjacent side. That's right here. Now, we have all the x components, right? What we're going to eventually do is say this is equal to this. We're going to set both of them equal to each other, right? Because that's what we're doing. We're saying momentum in the x direction initial is equal to the momentum in the x direction final. So this value has to equal this value, right? That's what we're going to do in a second. Now, let's focus on the y, right? Let's say the y direction. Same thing. We add up all the momentum in the y direction initially. Coming to our diagram, what's in the y? This car doesn't contribute anything to the y initially. This does, right? It has all of its momentum in the y direction. So we have 2,000 kilograms, 20 meters per second, positive, right? It's going in the positive y direction. That's positive. Same thing for momentum in the y direction final. Okay. Well, it's a collective, so the 3,500 kilograms total mass. And we need the y component of the final velocity, Vf sine of theta, right? Because we need the vertical y component of velocity. We do Vf sine is opposite, right? So we do this side of the right triangle, and that's this. Okay? And just like x, we say these two things have to be equal to each other. Okay, so let's write that down. What we're saying is that 1,500 kilograms times 25 meters per second has to equal 3,500 kilograms Vf cosine of theta. And this is also true. We're saying 2,000 kilograms, 20 meters per second is equal to 3,500 kilograms Vf sine of theta. Right? So two equations, two unknowns. Vf is unknown, the magnitude of the final velocity, we don't know what that is. And the angle, we don't know what that is. Two unknowns, two equations, perfect, we can solve it. Right? Different ways to solve systems of equations. If you ever see cosines and sines like this, there's a kind of a shortcut, right? What you want to do is just divide one equation by the other, because when you do that, you get tangent, right? So if you notice two equations, two unknowns like this, right, and there's a sine and a cosine, that's kind of a hint. You can take one and divide it by the other. So let's take the first equation and divide by the second one, right? So if I put this down here, 1,500 kilograms, 25 meters per second is equal to 3,500 kilograms Vf cosine of theta, right? So then this divided by this, what you'll see is that this cancels, we'll have to work that out. This is tangent of theta, right? So all of this drops out. You get tangent of theta is equal to some number that allows you to solve for theta, right? You can do that. Once you know theta, right, what you can do is come back to either of these two equations, either one works, put in that theta and then solve for Vf, right? And then allows you to solve for Vf. Does that make sense? Hopefully, that kind of strategy. So give it a shot, see what you get for the angle and the velocity here. Good to practice your tangents and angles in your calculator, right? Make sure degrees and radians, all that stuff is sorted for your exam, right? So you want to practice this. What questions do we have? You doing okay? Okay, switching over to the computer here, just looking ahead at what's coming up in the class. We're here, right? So June 24th, this is the Tuesday. We're covering more momentum, right? Collisions. We're going to get into fluids for a couple of days. Then on Friday, we're going to start talking about energy, which we're going to spend some time, a couple of days on, right? And then thermodynamics, and we'll get into simple harmonic motion towards the end of the class, right? Midterm 2 on the following Tuesday in a week, right? So where we're going to stop off is where homework 4 stops is essentially covering some of this, right? So not moments of inertia, but because you haven't had really a homework on it. Somewhere in here, I think so torque I said we'll talk about. So it should be about here, roughly, is where we're stopping. I'll send you more information about the midterm soon. You'll have a practice exam as before, right? So it'll be available in a couple of days, so you can practice that, right? So practice getting ready for midterm 2. And then we'll cover more material, and then the rest of it we'll cover with the final exam, right? So ask us questions on that discussion if you have questions about what's coming up ahead, right? And so, yeah, midterm 2, then we'll have the holiday on Friday next week, 4th of July, and we'll have one more week after that before we end.